Hi guys, you are welcome once again to the Smart Way lectures on the Science Ambassador series. This is a series of lectures we are running on all the areas in science, and today we are here with you to continue on thermochemistry. Today we are going to look at these questions. Okay, now let's begin with the first questions. It says that you are given the following exothermic reactions. Now we have the first one is ACl, hydrochloric acid, plus sodium hydroxide, giving us sodium chloride and water, that is the liquid water. And with the enthalpy, this the next one is we are giving ethanoic acid plus potassium hydroxide aqueous to give potassium ethanoate plus water. The next one, you are giving the ethanoic acid plus ammonia, and then we form the ammonium ethanoate. The last one, we are giving the H plus OH minus to get water, liquid. And these are the enthalpies for the reaction. So this is the enthalpy evolved out, and that is the enthalpy, and that is the enthalpy, and that is the enthalpy. Whereas that in our previous video we said that for every given reaction or acid-base reaction, there is amount of energy liberated to the surrounding. And depending on the type of acid, different amount of energy is what is liberated. We said that for strong acid, strong base, because there's a complete dissociation of all molecules, the energy liberated during the process is higher as compared to weak acid and strong base, or weak base and strong acid. And we said that the weakest of all is the what? Is when you add weak acid against weak base, the energy liberated is small, because some endothermic reactions are involved in the process which turn out to decrease the overall energy liberated. So we were able to explain that. So let's quickly look at which of the acids are strong, and then let's arrange them according to the amount of energy that will be liberated to the surrounding. So quickly let's look at that. Now we have ACl plus sodium hydroxide, and we know that ACl plus sodium hydroxide are strong acids, are strong acid. And so I have this one being a strong acid, okay, and then this being a strong base. I have this one being a strong base. I have this being a strong base. And so what happened during the interaction? They produce what? High amount of heat. In our last lecture we said that the value for the heat that they give out is almost negative 57.4 kilojoules per mole. So we said that so when strong acid against strong base react, the amount of energy they give out is negative 57.5. Now when you look at this one, we also have, this is a weak acid. So let me write for the previous one. Here we have strong, okay, we have strong against strong, we have strong against strong. Now this one we have what we call, this is ethanoic acid. In our last lecture I told you that all organic acid are weak acid, and this is an organic acid. And we said that for organic acid, this is the symbol for organic acid. They bear what we call this functional group. Organic acid bears this functional group. So when any acid that you see having this functional group, okay, having that functional group, okay, is organic acid. So let's have that in mind, that it is an organic acid. So this is an organic acid, okay, an organic acid, and specifically arachidonic acid. So this is an organic acid, organic what? Acid. And all organic acid, once again, are weak what? Acids, okay, are weak acids. So quickly there you can see from here that we have what we call the ethanoic acid, which is a weak what? Organic acid. So this is a weak organic acid, okay. So this is weak, this is weak, okay, this is weak, this is weak. Very good. And then let's go here. The other one, you have this one is a strong base. This is a strong base. Good. So let's go here. This is a strong base. This is a strong base. And so you have a weak acid reacting with a strong base. We have a weak acid reacting with what? A strong base. So what happened? Now the energy liberated during the process will be what? Will be less than this one. The energy liberated in the process will be less than this. So the first one will be the highest. Okay, the first one will be the highest. So the first one will be the highest. So let's give the first one order. this one, the reaction between ACl, okay, and this and sodium hydroxide, the reaction between AC and sodium hydroxide, which has an enthalpy of what? H1 will be the highest. So that will be the highest here. So you have the highest value. You have the highest. Okay. You have the highest. Now next is let's look at it before we conclude. So here we have what we call the weak acid reacting against a strong base. Now realize that for weak acid, not all the molecules dissociate, and so for complete dissociation to take place, some amount of energy is absorbed in the process to break down the remaining weak acid in order to dissociate. And because of that extra absorption of energy from the surrounding, it tends to decrease the overall energy given to the outside, and so that value is is lowered. Okay, that value is lowered. So here we have a strong. Here we have what we call this next one coming out. So this is it. Now, but before then, let's compare the other ones before we can now conclude. So we also have what we call this. So this will be weaker than this. Okay, the second one will be smaller than this. Okay, so this will be the smaller than this. Now quickly, let's look at this. From here you can see we have what we call weak and weak. Weak versus weak. Okay, so I have weak. I have weak base. Okay, and I have what we call weak I have weak acid, and I have what we call a weak base. So the two of them are weak. Okay, the two of them are weak. But here, one is weak and one is strong. So that means that the energy this one will produce will be higher than this one. Okay, that's why I didn't write this one. I didn't write this one here. So this will produce a higher energy value than this one. So let me write it here. We have what we call this one. Okay, plus ammonia. Now followed. So that is the evolve what we call enthalpy change, that is H2. And so this will be the next one. So this will be higher. This will be higher. And then let's go this one, because this is a weak acid against a weak base. What happens is that each of the molecules are not going to break down completely for weak acid and a weak base, and so more energy is absorbed from the surrounding in order to break down the undissociated acid and base. This this tend to lower the overall energy liberated to the surrounding. This will absorb more energy from the surrounding, and so it tends to decrease the overall energy liberated to the surrounding. And so the next one is this. The next one is this. That is this particular one I'm writing. Okay, then plus this one, and then that enthalpy is this. It's H3, and so this will also be the next. This will be the next one. Good. So the next one I'm going to look at is this one. Okay, the next one I'm going to look at is this. So quickly, what does it mean? Now we told you that for the definition of standard enthalpy of formation, we said that the amount of energy liberated when 1 mole of water is formed from 8 ions. Okay, that is H plus ion coming from a strong acid, and then OH minus coming from a strong base. And so because this, for 1 mole of water to be formed, it is always formed from strong acid and a strong base. Again, let me say it again. For 1 mole of water to be formed from any reaction, it always comes from a strong acid against a strong base. So these ones are the ions coming from a strong acid against a strong base. And so we have strong acid, strong base reaction right here. And so that will also fall in line with this, the second one, the first one. So that and that will all have the same rank. So that and that will have the same rank. So I have this one to also having equal rank with that. So this one, this and this will have the same rank. That is, I have what we call the H plus. Okay, the H plus reacting with the what? The OH minus. Okay. Yeah, so it will have the same rank, and then its enthalpy value, that is its enthalpy value is what? Is H4. That is H3, right? It's H4, yes, H4. So each enthalpy value is what? Is H4. So we have this one. So from the order, you can see that the highest the reaction that evolved the most energy to the surrounding is the first and then the what? The last one. The first and then the last one, followed by the second reaction, which is this, and then next the third one is the lowest. So the question is to arrange or giving what reasons the enthalpy in order of what? Decreasing what? Magnitude. So decreasing, that means from the what? From the highest to the lowest. So we are going to arrange it from the highest to the lowest. So let's arrange it from the highest to the lowest because it is decreasing. So let's do that quickly. So here, which one is the first one? We'll have what we call the H. We have what we call the H1. Okay, that is the first reaction, having the same energy as the last reaction, which is the same as what? H4. Okay, which is the same as H4. And so this and this are the same. Now followed by the third one. So this, from here we are moving to what? This is greater than the third one. So the third one we are moving to the CH. That is the change in enthalpy of the second one. Okay, the second one, this particular one. Okay, and then the last one, okay, will be this particular one, this particular one. So that's a weak acid against a weak base. So we are going to get the change in enthalpy of this. Okay, the change in enthalpy of that. Okay, so this is the reason. So very simple. Now the major reason that we have already explained is that for strong acid against strong base, because there is a complete dissociation of molecules, they almost liberate the same amount of energy. Now for weak acid against what? A strong base, the acid do not dissociate completely, and so extra energy is absorbed from the surrounding to break down the weak acid molecules, and which tend to decrease the overall energy liberated during the process. And here too, what do we have here? For weak acid against weak base, the molecules themselves do not break down completely, and so they absorb more energy from the surrounding in order to break down completely. This again tends to decrease the overall energy of the process. Very, very simple. So this is the answer. So let's quickly go to our next question. It says that outline briefly how you would determine experimentally the enthalpy of neutralization of ethanoic acid with sodium hydroxide. So that is outline briefly how you would determine the enthalpy of what? Neutralization of ethanoic acid with sodium hydroxide. We did this particular one in our last video, and so you just have to watch the video again and take your time and then extract the information from it. We'll end our lesson here, and in our next lecture we'll take what we call the standard enthalpy of solution. Thank you.